And okay, and the very first speaker is Aude Genevay. So Aude is actually quite, in my opinion, a rising star in the field. She previously did her PhD with Gabriel Perret on entropy regularized optimal transport for machine learning. She is now a postdoc in the geometric data processing group at the MIT. And she will talk today about comparing probability measures with optimal transport. And I think we're all super happy to have you as a speaker.
Thank you, Alison, for the kind words, and thank you for organizing this small workshop on optimal transport. So today I don't have a lot of time, but I'll try to give you an overview of different ways to compare probability measures and try to convince you that optimal transport is the right way to do so. And so I'll start by doing some review of general ways to compare probability measures, and then I'll dig into a bit more into my own research and the notion of distance that we introduced with my co-authors during my PhD. So comparing probability measures can be in different settings. So you can have either continuous probability measures or discrete ones, or a mix of both. And it's something that's really ubiquitous in many machine learning applications. So first, a first motivation in the discrete case would be quantization. So you have here in orange a first probability measures that has a large number of points. So it's a large point cloud, and you want to be able to summarize it with a smaller number of points. And so for that, you need to minimize some notion of distance between the orange point cloud, that's your data set, and the blue point cloud, that's going to be your summary of the data set. And so each of the point cloud is a discrete probability measure. And here, for instance, you want to solve the minimum for some notion of distance between measures over over the positions of the blue points. And so you want to find you're going to do, for instance, gradient descent over this problem in order to find the position of the blue points that's going to summarize your data set in the best possible way, so that you can still use this summary for inference tasks without having too much of a computational burden because of the huge point cloud here in orange. So that's motivation to compare discrete probability measures. Another motivation here that would be between a discrete and continuous measure would be density fitting. So again, you have a large point cloud here in some space, and you want to learn some probability measure alpha theta, so a parametric probability measure that is going to best represent your data set. And for that, again, you need to solve some minimization problem for some notion of distance d over probability measures. And you're going to minimize the distance between, so alpha theta, your model, and beta, your data set. And you're going to minimize over the parameters of your model. And so again, you're going to look for the optimal parameter alpha theta. So for instance, by doing gradient descent, so that's your model fits the data in the best possible way. So in both of these examples, I say you need to minimize some notion of distance between measures, but the question is, what is the right notion of distance to use for these problems? So I'm going to start by a review of classic notions of distance between measures and compare them and give the pros and cons of each of those. So probably the best well-known one would be phi divergences that were introduced by Cesar in the 60s. So for that, if you want to compare two measures, alpha and beta, for that you choose some convex function phi, and you compare the ratio of your densities with respect to that using that function phi. So more concretely, the best known example of that is the Kullback-Leibler or KL divergence. And for that, you use the convex function phi of x equals x log x. And so you can see that your KL divergence has this expression where you're going to look at the log of the ratio of alpha over beta. And so the problem is that if alpha and beta don't have the same support, the log here is not well defined. And so you're going to have something that's going to be equal to plus infinity. And so just to see in a very easy example why the KL divergence is not a good notion of distance for these minimization problems over the space of measures. So if you consider this toy example where you have here alpha is going to be a Dirac at 0, and you have a sequence alpha n that's a Dirac at 1 over n. since they have disjoint support, the KL divergence between alpha and alpha n is always equal to plus infinity. But you see that as n increases, the alpha n is getting closer. In some sense, it's very intuitive. You can see that alpha n is getting closer to alpha. But if you look at the signal that's given by the KL divergence, you get nothing. So if you try to take the gradients, to do the gradient descent over the KL divergence, you're not going to get a signal that's going to tell you that you're getting closer to alpha when n increases. And so the formal, I'm not going to get into too much detail here because I don't have time to get into that, but the formal notion here is that the KL divergence doesn't metrize weak convergence of measures. And so to avoid this kind of shortcomings of distances that don't have informative gradients, we need to find notions of distance that metrize weak convergence. So another class of distances that we can put on the space of measures are integral probability metrics that were introduced by Mueller. And for that, you choose some set of functions, f, and you compare your two measures, alpha and beta, by looking at the supremum over all the functions in that class of the gap between the expectation of f under alpha and the expectation of f under beta. So f is going to act as some kind of test function that looks at the difference between the expectation of f under alpha, the expectation of f under beta, and you look at the maximal gap that you can have for this class of function. And so depending on the class of functions that you choose, you're going to have different types of distances, and under very simple conditions over f, you get something that metrises weak convergence of measures. So for instance, if you take f to be the set of functions upper bounded by 1, you recover the total variation distance. So this one does not metrize weak convergence. But if you get the class of functions that are 1 Lipschitz, you get the 1 Wasserstein distance that metrises weak convergence. And if you take f to be the functions that are bounded by 1 in RKHS norm, you get something that's called maximum mean discrepancies. That's also something that metrises weak convergence. So I'll go back to the Wasserstein distance and the MD in a second. So maximum mean discrepancies were introduced 15 years ago by Arthur Gretton and co-authors, and they rely on the notion of reproducing kernel Hilbert space. So for those of you who are not familiar with it, the main thing to know about these RKHS is that any function in RKHS can be written as the scalar product of that function, of the representer of that function against a kernel K. And so K is going to be the kernel associated with that RKHS. So the kernel K defines the space. And so this property is very fundamental and very useful when you want to work with RKHS, the fact that you can decompose your function as a scalar product with respect to the kernel. And so if you take the integral probability metric, as I said, when f is the class of functions that are bounded by 1 in that RKHS norm, so that's the definition of the IPM that was on the previous slide. And if you use this trick that f can be decomposed as a scalar product between the representer and the kernel function, you can compute this supremum in closed form, and you get something that is the sum of 3 terms, and each term is the expectation over a product measure that depends on the kernel function for the RKHS. So you can see that here your maximum mean discrepancy between alpha and beta is just going to be the sum of the expectation of the kernel under alpha times alpha, the expectation of the kernel under beta times beta, minus twice the expectation over the product of alpha times beta. So if you get samples from both alpha and beta, so if you get 2 samples of size n for each of the measures, each of these expectations can be approximated by quadratic sums, and so you can get an estimation of MMD in quadratic time. So MMD are very efficient for that. You can that you have something that metrises weak convergence under very simple assumptions on K, and you have something that's computable in O of n squared. On the other hand, you have another more geometric notion of distance that's called optimal transport. So that's the theme of today's seminar. and it dates back to the 18th century. It was introduced by Monge. And so for optimal transport, so you have two measures, alpha and beta. You choose some notion of cost that tells you how much it costs to move a unit of mass from a point X in alpha to a point Y in beta. So it can be just a Euclidean distance or some more complex notion of cost. And you're going to look for a coupling pi that tells you how much mass you move from a point X in alpha to a point Y in beta. So here's a schematic representation of the coupling. So you have a probability measure here. And for instance, if you take this Dirac here, you're going to see here in the coupling matrix where to send it in beta. And so optimal transport consists in finding the coupling that has the minimal cost of moving all the mass from your first measure alpha to your second measure beta. And so formally, it's written as a variational problem here. So you're minimizing over the space of couplings with marginals alpha on one side and beta on the other side. So it's a constrained problem. You have two constraints that the coupling has one marginal alpha and one marginal beta. And so you minimize the total cost with respect to that coupling. And so when you take the cost to be some power of the Euclidean distance, then you get what we call the Wasserstein distance, and it's an actual notion of distance between measures. It satisfies all the axioms for a distance. So I've made kind of a review of all these notions of distance between measures. So I already told you why KL is not efficient because of this fact that it does not metrize weak convergence. But between MMD and optimal transport, which one should you choose? So if you look at the sample complexity, which is how efficiently you can, so it's a statistical complexity. So it tells you if you have two measures, two samples of your measures of size n, how fast it converges to the true distance between the continuous measures. So it's how good you can, how well you can approximate the distance using only samples. And so for MMD, this convergence rate is 1 over square root of n. So it doesn't depend on the dimension. While for optimal transport, your convergence rates degrades when the dimension increases. So we have what we call a curse of dimension. So if you try to estimate OT between probability measures and you use samples of those measures in high dimension, you're going to get a very bad approximation of the actual optimal transport distance. So that's 1 point for MMD and 0 for optimal transport. On the other hand, on the computational side, so for MMD, I told you that it essentially boils down. So computation, it means if you have two samples of size n, again, what's the computational cost in terms of computational algorithmic complexity. So for MMD, it essentially boils down to computing these expectations over product measures. So it costs you n squared. It's essentially double sums. And for optimal transport, you have this constrained optimization problem. And so you need to solve a linear program. And this will cost you n cubed log n. So you can see that again, on the computational side, MMT performs better than optimal transport. So when you see it like that, you could see, well, let's forget about optimal transport. MMD is faster to estimate. It's more robust statistically. So why do we still want to use optimal transport? Well, I'm going to show you on a simple example, a case where MMD fail and optimal transport does very well. So here, and I want to minimize the distance between the 2 point clouds, and the minimization happens over the positions of the blue points. And so I'm just going to do gradient descent to solve this problem, with D being either MMD or optimal transport. So here's what I do MMD. You can see that it recovers very well the more dense part of the orange point clouds, but the more extreme positions are not very well recovered, and I have these blue points that are lingering in a place where I don't want them to be. If I do that for optimal transport, I get a very efficient recovery of my orange. It shows the same number of points for the points. And so what I want is exactly for the blue points to cover the orange points. And it happens when I use OT. It doesn't happen when I use MMD because the gradients are too weak to get the blue points to the more extreme orange positions. And here's more striking on a bit more complicated example where I have two orange, my orange point cloud is separated in two, and I do the same thing. So for M and D here, it's completely going to fail to the orange positions. So you can see that here in this case, with a bit more complex geometry, MMD is really performing poorly. While for optimal transport, I do my gradient descent and I get an immediate matching of the blue points to the orange points. So it's taking a while to get there, but it's working very efficiently. So you can see that over the good point would be that it has better gradients. It's more efficient for these minimization problems. So ideally, we would like to be able to use something that has the same geometry as optimal transport, but with a better computational cost and a better sample complexity. So there's actually an answer to that problem, and it's performing entropic regularization of the optimal transport problem. So it was introduced at least to the machine learning community by Marco Couturi in 2013. And it consists in taking so this is the optimal transport problem, so minimizing the total cost with respect to a coupling. And on top of that, you add an entropic regularization. So here epsilon is the regularization parameter. And H is the entropy of your coupling with respect to the product measure alpha times beta. So here, so what happens in practice when you physically? So instead of having a very sharp coupling, so if you remember the coupling matrix from when I introduced optimal transport, so you imagine that you have one measure alpha on this side and one measure beta on this side. So your couplings just tells you the correspondence between the points in alpha and the points in beta. So when you have a small regularization parameter, so you're very close to the standard optimal transport problem, you still have a very sharp matching. And the more you regularize, the fuzzier your matching gets. So instead of matching 1 point to 1 point here, you're going to match 1 point in alpha with a region in beta. So it gives you a fuzzier matching. And so why do we enjoy using this entropic regularization? It's because it has a more simple dual formulation. So it's a bit technical, but if you look at the convex dual of optimal transport, so the standard optimal transport, the dual is the maximum. So instead of having a minimization problem over couplings, you have a maximization problem over functions, where each function corresponds to a marginal. So U corresponds to the constraint that one marginal is alpha, and V corresponds to the constraint that one marginal is beta. And this problem is still constrained. You have the constraint that U plus V is smaller than the cost functions. So for instance, the Euclidean distance between X and Y. If you look at the regularized optimal transport problem, instead of this hard constraint here, you have an exponential penalty. So with epsilon, your regularization parameter, and you're penalizing the fact that U plus V is smaller than C, is larger than C, but with an exponential. So it's essentially a smoothed out version of the standard dual. But what's nice here is that we get something that doesn't have a constraint, and so it's easier to solve. And you can see that we have a maximization problem that is concave in U and V. And so an intuitive way to solve this is to alternately maximize over U with fixed V and maximize over V with fixed U. And this algorithm is actually known as Sinkhorn's algorithm in the literature. And so it's so here it's written in the discrete setting. In the discrete setting, it simply boils down to doing a matrix vector multiplications, where the matrix K here encodes the cost function, the cost information. So if you have 2 point clouds indexed by xj, so alpha indexed by xj and xi, sorry, and beta indexed by yj, you compute all the cost functions here, and you encode that information in your matrix. And then to compute your minimizer U and V, you're just going to have to do matrix vector multiplications. So you can prove, and it has been proved, that this algorithm converges to the actual solution of the problem. And each iteration has a complexity O of n squared. So you can get a complexity that's similar to that of computing MMD. Whereas if you wanted to compute standard optimal transports, you had something that was that had a cubic complexity. Of course, there's no free lunch. Okay, if you're taking the regularization parameter that goes down to 0, you're getting back closer to the true optimal transports. The convergence rate, so the number of iterations that you need to do for your synchronous algorithm to converge gets prohibitively large, and you're not going to win anything in the end. But if you regularize enough, you can of this very fast approximation of optimal transports. So that's for the computational side. Okay, we have something that's efficiently that we can compute efficiently. And for the statistical side, so we're going to look at the sample complexity. So it tells you how well you approximate the distance between measures when you compute it using samples of the measures. So we know that for optimal transports, so if you look at the Wasserstein distance between alpha and beta, and the Wasserstein distance between alpha n and beta n, that are empirical measures for alpha and beta, you get a rate that's n to the minus 1 over d. So it means when the dimension increases, the number of samples that you need to reach precision increases exponentially. That's typical of the curse of dimension. And for MMD, as I mentioned earlier, so if you look at the same quantity, it scales as 1 over square. Natural question to ask is what happens when you look at the, and we were able to prove a couple of years ago that you get kind of an interpolating behavior for entropy regularized optimal transport. So when the regularization parameter is small, you're close to optimal transports. You get a 1 over square root of n convergence rate, but with this bad dependence here on dimension. But when epsilon is large enough, you have the same rate as MMD. So if you have large enough regularization, you break the curse of dimension. So regularized distance that is fast to compute, that has a good sample complexity, but if we use it for minimization problem here, you can see that what you get is not very efficient. Instead of having the blue points that cover the orange points, we have something that collapses in the middle. So what happens, it's the effect of entropy. If we regularize too much, we have the points that the blue points that will collapse to the mean of the point cloud. So the problem is that we would actually want to be able to regularize enough, because the more we regularize, the faster the synchron algorithm is, and so the faster it is to estimate optimal transports, and the better the sample complexity is. And so we want to be, so I'm going to skip those slides, but essentially the more you regularize, your approximation of optimal transport is, and so you can't really you benefit from good statistical and computational properties, but you don't have the good geometric properties anymore. So the idea that we had to alleviate this shortcoming is to introduce something we call synchron divergences. And so it was simply a way to make sure that when we look at the regularized Wasserstein distance between alpha and itself, we would get something that is equal to 0, which was not the case before because of the additional entropy term. And so we just, what we call synchron divergences is the sum of 3 terms. So the first term is the entropy regularized optimal transport. And the other 2 terms are kind of corrective terms to make sure that when you look at the synchron divergence between alpha and alpha, you'll get something that is equal to 0, okay? And so this very naive idea at first is actually quite powerful, because you have something that you have a new notion of distance that interpolates between optimal transports and those maximum mean discrepancies. So when epsilon goes to 0, you recover the Wasserstein distance.
But when epsilon goes to infinity, you recover MMD with some specific cost function, with some specific kernel for the MMD that is going to be minus the cost function of optimal transport. And to make sure that what you get is a well-defined MMD, you need to make sure that your cost function satisfies some properties, but those properties are satisfied for the Euclidean distance with a power smaller than 2. In that case, MMD is what we call the energy distance. And in subsequent work, there's colleagues from INS with, in particular, Jean, who's going to give a talk a bit later, who proved that the synchron divergences are positive definite. And so they, it's actually something that is going to be equal to 0 if and only if alpha equals beta. So it was originating from a pretty naive idea, but then it turns out to be something that's quite powerful in practice. And as you can see, if so here's what happens when we use the energy distance. So it's the MMD with the Euclidean cost. So it's the same as I used in the introduction for MMD. You still have those blue points here that are lingering. And here's what happens, here's what happens when you use synchron divergences. You get something that's pretty efficient. So you are able to regularize with a medium regularization parameter that allows you to have a fast enough approximation. But since you debiased with the synchron divergence, you don't have the points that collapse to the mean as they did previously. And even if you look at the more complex example with the 2-point clouds, you have something that is much more efficient than MMD at recovering the geometry of the orange point cloud. So here's a summary of the different notions of distance, maybe that will be more clear. So here's the initial setting with the orange point cloud, and that's the target, and the blue point that's initialized. So when you use entropy regularized optimal transport with, for instance, a regularization parameter, here medium strength, I would say, epsilon equals 1, you have the blue points that collapse to the mean of your point cloud. If you debias using synchron divergence with the same regularization parameter, so it means in terms of computational complexity, those two are roughly the same, you get something that's much better at recovering your orange point cloud. And of course, if you take your regularization parameter to be too large, so your algorithm will be a bit faster, but you'll converge to the MMD as the interpolation property tells you. And so the extreme points here will start to not be where you want them to be. And in the limits, you recover the energy distance or the MMD with the Euclidean cost. So here I show you example on point clouds because it's easy to understand and to and it's nice to visualize, but you can also do it, of course, on much more complicated examples. So here's still a toy example, but it's an ellipse in 3D. So you start from you have blue points here that were generated uniformly inside of an ellipse, and you want to learn the ellipse that generated these points. And you can do gradient descent over the parameters of the ellipse and try to recover the generative models for these points. And so here's what happens when you use optimal transport as a distance between your point cloud and your model. So regularized optimal transport has this problem of collapsing to the mean. But if you debias using synchron divergence, you recover the generating ellipse in a very nice way. And here's a comparison of the energy distance, or MMD, versus synchron divergence. So if you try to estimate the covariance and the center of the ellipse, synchron divergences has a better performance than energy distance. So here I just showed some easy examples in 2 and 3D, but you can move on to much more complex generative models of, for instance, images, like GANs, for those of you who are familiar with it. So the model you're going to learn is a much more complicated neural network that is going to generate images. And so you want, again, to minimize the synchron divergence between your generative model alpha theta and your data beta. And for that, you just generate images with your generative models. You compare them to your data sets, and then you can backpropagate. You can backpropagate your gradient through this whole scheme and do gradient descent over the synchron divergence, because these synchron iterations here are fully differentiable. But I think maybe Jean is going to tell you a bit more about how to do these things efficiently. And so I'll wrap up because I think I'm already over time. The take-home message from this talk is that synchron divergences are a great notion of distance to use between measures. So they're a way to debias the regularized Wasserstein distance. They interpolate between optimal transport for small epsilon and MMD for large epsilon. So for a small regularization parameter and large regularization parameter. And they allow you to get the best of both worlds. So you have the good geometric properties of optimal transport, in particular those strong gradients that allow you to solve minimization problems over measures efficiently. And you also get good statistical properties, as you can break the curse of dimension if you regularize enough. And of course, what's crucial for machine learning applications is that these synchron divergences can be computed with fast algorithms to implement them, just as you can do for the regularized Wasserstein distance. Well, thank you for your attention. I'll be happy to answer any questions you may have.
Thank you so much, Aude. It was super nice watching your presentation. I'm sure that people already have some questions. So for instance, Francisco does have one. Francisco, you can unmute yourself.
Oh, hello, can you hear me?
Yes.
Cool, yeah, I'll just read them out. So this is just right at the beginning of the presentation when you were talking about the issues of the KL divergence. So I just wanted to ask, in the context of like a semi-discrete problem, right, saying we're doing maximum likelihood with a parametric model, or we're doing something like variational Bayes, is the issue of the Rn derivative being undefined an issue in these practical applications? Because, you know, there's, like I mentioned earlier, there's proxies to minimizing KL divergence in these things, like the free energy or the maximum likelihood, and these things don't, the empirical estimates of these quantities don't explode, and they also converge. They're consistent. They converge in probability to actually minimizing KL between the two continuous, or the two measures, the two fully supported measures. So yeah, I was wondering, you know, is this something I should be worried about when I'm doing maximum likelihood, or when I'm doing variational Bayes, or is it really not a problem?
So that's a good question. So I know that KL is still used a lot in the Bayesian community. It's because it has KL has a lot of easy computational properties. Like you can compute a lot of things in closed form with KL that you can't really do with optimal transport. I think KL works as long as you're working with probability densities. But if you start working, for instance, with the generative models, so when you start from like a small dimensional space and you push it forward through like a complex neural network, you get some models that are very degenerate. So you don't get like nice Gaussians or well-defined densities. And then it's you can easily apply optimal transport or MMD or synchron divergence, but KL is going to be much harder to use in those kind of degenerate cases.
Yeah, no, that makes a lot of sense. Like with GANs and anything that's like implicit distributions, it's quite clear. But for example, if we look at maximum likelihood, it sort of has this setup, right? So if you look at maximum likelihood, in the limit in probability, it's minimizing. It's the same as minimizing KL divergence between the true distribution and the parametric model. But of course, in practice, this is not what you're doing, right? Because if you wrote down KL divergence between the empirical distribution and the model, this doesn't work. This is undefined in the measure sense. But you know, it converges in probability if we do maximum likelihood instead. So this was sort of what I was building on the question, like, you know, is this something I should be worried about? Is this something I take for granted? And it is sort of similar to a degenerate case, right? Because you have a discrete empirical distribution, you have a parametric model, and you are minimizing KL divergence in a proxy sense, at least.
Yeah,
it does converge to that.
Yeah, so I think that's actually a good question. I don't think I have like the perfect answer to this question. So of course, maximum likelihood has been very well studied, and we know that it's like robust and has all these nice statistical properties. So the thing is, I think that might be a problem is if you do gradient descent on these things, like the gradient of the KL divergence won't be as efficient, or won't give you as much signal as the gradient of optimal transport, for instance. So I think that's where the maximum likelihood approach might be failing. But if you're just directly minimizing like in closed form or something, I think maximum likelihood would still be very efficient. And we know that the maximum likelihood estimator has all the best things you can ask for in a statistical sense.
Yep, no, that's a great answer. Thank you. That's helpful. I have another question, but if someone else wants to ask a question, I can wait.
No, go for it. But that
okay.
might be the last question.
Okay, sure. Yeah, so for the sample complexity of the Synchron algorithm, what are the assumptions that the cost function? So you know, in the context of OT, the cost function is a metric of some sort. But is this a required assumption for the sample complexity rates of the Synchron algorithm? Because you could think of something that's not a proper kernel, for example.
So you kind of have two ways of looking at the assumptions for these sample complexity problems. So you can either consider that you're on a bounded space and that your cost function is differentiable. So that's one way to, so that's one kind of assumption. Or the other kind of assumption is to have, to make sure that the integral of your cost function against your measure is bounded. So that would be the same as assuming, for instance, sub-Gaussianity with a cost function that's the Euclidean distance.
But is symmetry required, or no, positive definite of the kernel?
Symmetry is not required. You just need to make sure that essentially the integral of your cost function against the measures over your space doesn't blow up, because the way to prove these things is essentially to control the Sobolev norm of the solutions of the dual optimal transport problems. It's a bit technical, but what we end up doing is looking at in the proof is we come up with the integral of the cost function, of the derivatives of the cost function against the measures. And so that's the thing we need to control in Sobolev norm. So yeah. So we just need to make sure that we have a smooth enough cost functions, something that doesn't blow up, but that's very weak conditions.
And does it have to be differentiable, or is just Lipschitz conditions enough?
So yeah, it's easier to prove if it's differentiable, but you can still prove it, for instance, for the L1 norm or things like that. So I think sub-differentiable is enough.
Okay, that's great. Yeah, thanks so much. That's very helpful.
Thank you so much again, Aude, for the talk. And now I think we will move on with Anton Mallasto. So Anton, can you, for instance, share your screen and see if it's working?
Yes, sure.
Okay, perfect. So yeah, actually, so just to present Anton, he's quite well known here in the Coxie section. He was previously doing his PhD with Åsa Ferhagen at Copenhagen University on geometric method in probabilistic modeling. And he also did actually a research stay with Marco Couturier. He is now a postdoc at Aalto University in the probabilistic machine learning group. And his talk will be about Bayesian inference for optimal transport with stochastic cost, and this sounds super exciting. So thank you for the talk.
Thanks for the nice introduction, and thanks for inviting me to give a talk here. It's always nice to visit Lyngby, even if it's remotely like this. Right. So does my screen sharing work? Are the slides changing? Great. So an overview for the talk. So again, we'll talk a little bit about optimal transport, which will be much easier for me after Aude's very nice introduction. Then we will kind of change the situation a little bit by making the cost function in optimal transport stochastic. And then when we have this stochastic problem, we'll kind of study how to use Bayesian inference for solving this stochastic optimal transport problem. So here's a little bit of repetition. Hope you don't mind, but just to fix notation after Aude's talk. So I will be focusing on the discrete setting. where you have in the optimal transport problem 2 measures mu and nu, and then you have a cost matrix. So here we have visualized the OT problem. So we have the 2 measures mu given in blue, where we have 3 atoms here, and then we have the nu in red with 4 atoms. And then we have the cost matrix C, where each entry tells you the cost of moving mass from, let's say, x1 to y1. This x's here should be y's. Sorry for that. And then the OT problem in the discrete case can be written as minimizing an inner product. So you take your cost matrix C, and then you take this gamma matrix, and then you take the Frobenius inner product between the 2 matrices, which is exactly the same as taking the Hadamard product between the matrices and then summing over all of the coordinates. And then you minimize this with respect to gamma, which is the joint distribution or the transport plan, which is constrained to lie in what Aude called couplings. I will call this set as the transport polytope. So it's all the set of matrices where their rows sum to the elements of mu and the columns sum to the elements of nu. So it's just the joint distributions. And for this problem here, when we solve the optimal transport problem, we get this optimal transport plan here. And this gamma here is also illustrated in this figure on the left, where these magenta lines tell you how the mass is optimally transported between the points. And the thicker the line is, the more mass is being transported. And then when we find the optimal transport plan, well, then it's called optimal transport plan. But if we just have any gamma belonging to this transport polytope, we call it the transport plan. And if it's the optimal one, then we kind of emphasize that. Yeah. So now we'll introduce this setting with a stochastic cost. So I hope this animation is working for you. So here, what's changing is that the C here now will be stochastic. That comes from some distribution. In practice, what will happen is that we will get some samples from this cost distribution. There's essentially 2 natural ways for how this setting arises. The first one is that the cost function is kind of intrinsically stochastic. For example, when you're driving between 2 locations, then depending on the traffic congestion, it takes different amounts of times to go from, let's say, from Lyngby to central Copenhagen. And that's why kind of you use a different amount of gasoline for your transportation. And that's why kind of the cost is stochastic. Another setting is here where we kind of have these hierarchical measures. So we have the mu assigns mass over these different symbols, so x, sphere, and the square. And that's kind of the first probability distribution that we have. Then we also have other distributions, kind of the spatial distributions for the symbols. So the mu the mu masses stay the same all the time, but every time we look at the problem, these kind of locations of the atoms change. And here is the kind of how the cost matrix changes as the locations of the atoms change. And this, of course, propagates into the transport or the optimal transport plan here on the right. I hope it's visible because I have some zoom window on top of it for my screen. But as the cost matrix changes, also the optimal transport plan changes. So now what we want to do is that given samples from the cost matrix C, we want to infer the distribution over the transport plans or the optimal transport plans. And well, before we solve the problem, let's motivate it a little bit. So as I already mentioned, one example in real life transportation or logistics, stochastic cost is always there depending on kind of the varying traffic conditions. Then another example, this is a little bit more hypothetical, is that if you're transporting goods between uncertain locations that are on the move, for example. So let's say you have, I don't know, you have some electrons buzzing around, and then you want to transport mass between those electrons, but you can never know where's the location of the electron, but you will still kind of be able to match the two electrons with each other for the optimal transportation. So that's one example. And the last example is that kind of the stochastic setting allows for uncertainty quantification in optimal transport models. And especially it kind of allows us to use optimal transport in situations where we don't have full information. So when kind of we're not that sure about our cost, or if our cost is somehow artificially created. Yeah, so we'll tackle this problem using the Bayesian framework. So in the Bayesian setting, as we want to infer a distribution for gamma, the first step is to kind of gather all your prior information on gamma. So you need to define a prior distribution that we denote by this on gamma. Then we need to sample the cost matrix to get the sample ck, where k runs from 1 to n. And then we need to define the likelihood of kind of how a given transport plan gamma relates to a given cost ck. And we do this by defining the so-called auxiliary optimality variables OKs, which were first, I think, introduced in the literature of maximum entropy reinforcement learning. So OK here equals 1 if we take, given a transport plan gamma belonging to the transport polytope, if it minimizes the total cost given ck. So this Frobenius inner product here is again just the kind of total cost that we get if we have this cost matrix ck and we transport the mass using gamma. And if it's not optimal, if gamma is not optimal for the ck, then OK equals 0. And for this kind of we pick this likelihood in equation 3. So given the cost matrix sample ck and transport plan gamma, then OK equals 1 with probability of exponential of minus the total cost. And why do we consider this kind of likelihood is motivated here. So the smaller the total cost is, the more likely gamma is optimal for a given ck. So that's why kind of we have this minus here. The smaller this total cost gets, the higher this probability gets. On the other hand, let's assume that our cost function is always positive. Then also the optimal transport cost will always be positive. And so if the total cost equals 1, then gamma has to be optimal for ck, because we cannot find any gamma so that this total transport cost will be negative. And that's kind of, yeah, if this total cost here is 0, then this probability equals 1. And that's kind of why we use this model of likelihood. But you will pick your own model, kind of form for this likelihood. Now that we have the prior and we have the likelihood, we can use Bayes formula to compute the posterior likelihood for the transport plans. And we essentially have two natural ways of doing or computing this posterior likelihood or defining it. The first one is to condition gamma to be optimal for all of the cost matrix samples ck. And this yields the posterior log likelihood using Bayes formula in equation 4. Here you have to do some assumptions, for example, that the event of gamma being optimal for different ck's, this should be independent. This, of course, isn't the case in practice, because a given gamma can be optimal for an infinite amount of different cost matrices. But taking this assumption, we can derive this form for the log likelihood, for the posterior log likelihood. So looking at this, first we have this just log prior probability of gamma. And then we have the total cost, transportation cost, where the cost matrix is given by the sum of the samples and then the transport line is just gamma, and then some constant. Now this, for people working in optimal transport, this looks kind of familiar, this expression, and this is very related to when Aude was talking about the entropy regularization of optimal transport, because this here, if we solve for the maximum a posterior estimate, that is gamma that maximizes this log likelihood, then that's exactly the same as solving regularized optimal transport with the regularizer given by this log prior likelihood of gamma. So for example, for the entropy case, if this minus log prior gamma, if this equals the entropy of gamma, then this is exactly the same as solving entropy regularized optimal transport. If you have a Gaussian likelihood here, then this is the same as quadratically regularized optimal transport. Another way how we can condition gamma is to condition it to be optimal for some CK, in which case we get this posterior log likelihood in equation 5. So what's happening here is that we get the same log prior gamma term here, but we also get this log sum expression for the total cost given samples and the gamma. And kind of intuitively, what this expression tells us is you have to recall that this log sum exp is a way of defining a smooth minimum over these entries, this total costs here. So you just have the log prior gamma, and then you have the minimum of these total costs here. Well, a smooth version of it. So kind of when you compare the two posterior ways of conditioning gamma, here you just kind of study the average case when gamma is just kind of on average, it's optimal. And here, when you're giving gamma, then you're only kind of interested in the cost matrix that makes gamma be optimal. Right. Now that we have these posterior log likelihoods, then in the Bayesian framework, you have to then sample from these posterior log likelihoods, or these posterior distributions. And that's kind of the tricky part here, because gamma has to be constrained to lie in the transport polytope. The nice thing is that the transport polytope can be cast as an affine, kind of a subset of an affine plane, so you can linearly parametricize it. But you just have to make some constraints so that you don't sample outside of the transport polytope on the affine plane. But that you can just do by defining a prior likelihood that has its support inside of the transport polytope. But there's still a problem that we cannot really get over, and that's the dimensionality of gamma. So if mu has n atoms and nu has m atoms, then gamma will have the size of n times m. And as n and m increase, that increases very fast, and Bayesian sampling or sampling in high dimensions isn't that effective. So kind of what we did was just use Hamiltonian Monte Carlo to sample on the affine plane. But I because of the lack of time, I will just skip all these technical details on the sampling. So here's some examples then. I hope this is working. Yeah. So for the toy example that we saw earlier, the kind of maximum a posterior estimate is given here, which is very similar to the kind of OT solution we saw earlier on the first slide when we were introducing optimal transport. And then here on the right, we have samples from the posterior. And here, the kind of, I think that the prior distribution we used was the entropy prior. Another example is given by MNIST. So here what we do is that in MNIST you have pictures of digits. We divide the digits into two groups, from 0 to 4 and from 5 to 9. And then we assign form these two groups into probability measures by assigning some probability mass over them. So we'll just say that these have uniform probability mass. Now, if we have two probability measures and then we want to transport the probability measures to each other, and for that we need a cost. So a natural way of defining cost between, let's say, the digit 0 and 9 is to sample images of 0 and 9 and then compute, let's say, the L2 distance between those images. But each time you sample an image, the distance will change. And that's why we arrive at this stochastic OT setting. Well, anyway, as we solve the stochastic OT problem, we visualize the resulting posterior distribution by this matrix of images. So each cell in this matrix is the histogram of that mass assignment. So then when you have the transport plan gamma, then this will be the gamma 05 or 00 cell, and this will be gamma 01 and so on. In the black dashed lines, you have the map estimates, and the blue histograms are just the histograms of the distribution. And the results here are intuitive. 4 is usually mapped to 9, but there's also cases when you map it to 7 or 8, you rarely map it to 5. Then here on the left, we conditioned gamma to be optimal for all of CK, and on the right, we conditioned it to be optimal for some of CK. And it seems that in this MNIST case, there isn't really a big difference between the two. And that might be because there isn't that huge of a difference between the cost matrices that we sample. Then another example is given by the US presidential elections. So we have data from Florida in the year 2012. So for each county, we have data that tells us the mass distribution or the vote distribution for different parties. So how many votes did the Republicans get? How many did the Democrats get? And then we also have the vote distribution for different ethnicities. And then a question in social sciences is that given these two marginal distributions, what is the joint distribution? That is, how many votes did the Republicans get from ethnicity A, or how many votes did Democrats get from ethnicity B? So the problem is to solve this or infer this joint distribution from the two marginals. Now, there isn't a natural way of defining a cost here, but you can use additional information to define a cost matrix. So then we arrive at the realm of optimal transport. Here in this figure, on the x-axis, we have the ground truth mass assignments of the transport plans. So each x point here is a gamma ij, where gamma is ground truth joint distribution for how the ethnicities voted different parties. And then on the y coordinates are then given by our inferred vote or votes voting pattern. The means are given for the posterior distribution are given by the dots. Then we have the two standard deviation intervals given by the blue lines. And as you can see, the method is able to infer on average how the voting happened between the ethnicities and parties, but also what stochastic OT gives here is the uncertainty here. And as you can see, the further away the points or the averages are from the real ground truth, the more uncertainty there is. So clearly this uncertainty that we get here in this setting is important and actually useful in practice. And then last example, we have a New York City taxi data set. So we have a data set that tells us information on trips between different zones. So we take Manhattan and we divide it into 15 different zones. We have 5 pickup zones in blue, and then we have 10 drop-off locations in red. And then we have a distribution of passengers over both of these zones, illustrated using these different shades of blue and red. And the problem is then that we have a demand of passengers in these red zones, and then we have a supply of passengers in these blue zones, and we don't really care about where the passenger wants to go. We just need to kind of fulfill this demand and send passengers using the taxis. So now we have two marginals, and the cost matrix then to define that, to define the cost between two zones, we sample a trip from the dataset between the two zones. We take the total fare of that trip, so kind of the dollar value, how expensive it is, and then we divide it by the amount of passengers on board. So the cost between two zones will just be a random cost that tells us how expensive in dollars it is to transport one person between the zones. And then kind of here again, we have illustrated these histograms, and here the red one is kind of average case analysis, and the blue ones we get from conditioning the transport plans to be optimal for some of the cost matrices. So there's kind of some interesting cells here. For example, when you look at this cell, what the transport from 1 to 13, which is from here to here, then on average, it's very kind of profitable to move people between those two zones. But there is also a variation, so that not always, when you look over all the trips, it's smart to move the passengers between these two zones. But you also have this trend that the higher the average case assignment is, the more diverse variance you have in the histogram over the posterior distribution. But there is also cases where these kind of where the average case and this histogram differ by a lot, which is, for example, between the zones 3 and 14, where 3 is here and 14 is here. So this might be because when you look at the average case, you might get that this is smart to transport here. But then you might have a lot of situations where it's not actually smart to kind of transport between these 2 points. And that's why kind of you get this big difference here between our posterior distribution and the kind of average case analysis. Right. Yeah, that's it. I still have a summary slide. So stochastic cost in optimal transport induces stochasticity also on the transport plan, resulting in a transport plan distribution. To sample from this distribution, we can use Bayesian inference, but to do this, we need to define first a prior for the transport plans, and then a likelihood that associates a transport plan to a cost matrix sample. And then the resulting framework allows applying optimal transport in settings with uncertainty. And this, at least to my knowledge, is something that hasn't really been studied before. Yeah, that's it. Thank you.
Thank you a lot, Anton. It was super interesting. We might have time for 1 or 2 questions if people have some questions from this talk. Okay. You can unmute yourself if you have any question. Otherwise,
hi, Anton. Hi. It's Aude. Yeah. So first, it was super interesting. I wasn't really familiar with this line of work, and I think it's a super interesting problem. And I was wondering if, so here you have a stochastic cost function. Is it easily extendable to stochastic positions of the measures, for instance, or is it a completely different problem? Is it something you've thought about?
So it's the setting where the marginals are stochastic.
Yeah, for instance, yeah.
Okay. Well, I guess this is applicable when the kind of atoms of the measures are stochastic, like in in the examples I gave. But if the mass distribution over these atoms change, so when kind of there's a lot of uncertainty in the marginals, then we haven't really thought about that setting. So kind of if the marginals move around in a nice way without changing the mass distribution, then this is applicable. But if it changes, if the mass assignment changes a lot, then I'm not really sure how to do. I guess it would complicate the Bayesian sampling, because then so here in this setting, kind of we have a fixed transport polytope. But if we start changing mu and nu, and if they're stochastic also, then this transport polytope will also be kind of fuzzy. And that will complicate things by quite a lot. I hope that answered your question.
Yeah, thank you.
Thank you.
Any more questions? Okay, so thank you again, Anton.
Thank you.
So last but not least, we are very lucky to have also Jean Feydy joining the seminar. So Jean was previously a PhD student at the ENS under the direction of Alain Trouvé. He was interested in computational anatomy, optimal transport theory, but also geometric data analysis, and is now a postdoc at the Imperial College London under the supervision of Michael Bronstein. Most importantly, he developed a library called KOPS, which speeds up the computation and could be used for instance, large-scale optimal transport. And he will talk about fast geometric learning with symbolic matrices. So whenever you want, Jean, you can share your slides. I think, are you mute? Oh.
No, we can
I cannot hear you. I am the only one.
I can't hear Jean either. So
yes, with this microphone maybe.
Yes, yeah, it's
it
working.
works. Okay, perfect. Thank you. Okay, no, I have like 4 different mics on this laptop. So, okay, so I mean, thank you very much, Alison, for having invited me, obviously, and for you all to be here. So let me share my screen, and we'll start. Okay. Okay. So as Alison told you, I'm at Imperial College London now, and essentially I'm here to present to you 2 libraries, which are called KEOPS and geomloss for optimal transport, that enable fast geometric learning with symbolic matrices. So this is all joint work with many really very good friends and researchers, most importantly Benjamin Charlier and Joanne Glonès for the numerical foundations, Thibaut Séjourné, François-Xavier Vialard, and Gabriel Perret for the optimal transport theory. And for the applications, Pierre Roussillon, Pietro Gori, Alain Trouvé, so my PhD advisor, and more recently, Freyr Sverrisson, Bruno Correia, and Michael Bernstein for applications to protein sciences. So when you look at this title, maybe you wonder, what on earth are symbolic matrices, right? And what is the link with optimal transport theory? To understand what I'm getting at, I want to talk a little bit about the type of code that we all write on a daily basis using Python machine learning libraries. Okay. As you know, those frameworks, so PyTorch, TensorFlow, NumPy, or JAX, always represent objects using tensors. So dense matrices, large contiguous arrays of numbers. This representation is very convenient and has been well supported for decades. We're all familiar with them. But there's a big downside, which is that using large matrices every single time we want to define an object puts a heavy load on the memories of our GPUs, with time-consuming transfers that take place first between the CPU memory and the GPU memory, but also on the chip itself between the main GPU memory and the many compute units, the CUDA cores that you buy when you buy a GPU. So this is a big problem, and it means that in practice, most of the programs that we write, either in applied math or in deep learning, are memory bound, which means that we spend more time moving memory around on the GPU and within the GPU than actually making mathematical computations, which is a shame. Okay, so to work around this problem, a common option is to rely on sparse matrices. Okay, tensors that have few non-zero entries and can thus be represented using lists of coordinates and coefficients. This solution is elegant and allows us to represent large tensors with a small memory footprint. But there's also a big downside, which is that GPUs are not really hardwired, at the silicon level to manipulate those kind of objects, which means that to get real speed up when using sparse matrices, you need to have a very, very sparse matrices with, let's say, less than 1% non-zero coefficients. This is very restrictive, of course, and means that outside of graph processing, few objects are really sparse enough to benefit from this trick, from this representation. Thinking about it though, most of the large arrays that we manipulate, as researchers, applied mathematicians, share a common computational structure. We can represent, distance matrices, kernel matrices, point convolutions, or attention layers can all be described as symbolic matrices. Given relatively small data arrays like xi, yj, so point clouds or feature vectors, the coefficients of these big matrices at location ij are given by a mathematical formula f that is evaluated on the points xi and yj. So think, for instance, of the Euclidean distance or the squared Euclidean distance between 2 points xi and yj. This means that in a computational sense, you can represent the same big matrix using only a symbolic object, so a symbolic formula, and the relatively small data arrays here and there in red and green. This means that you can manipulate the same object with a linear memory footprint because you never store in memory a large quadratic array, and also gives us at a low level the opportunity to optimize the use of registers of very fine-grained memory layers that enable in practice a speed up by 1 or 2 orders of magnitude compared with the standard PyTorch GPU baseline. But we'll make this clear in a few minutes. So my work is primarily centered around providing support for this new abstraction on the GPU with all the perks of a deep learning toolbox. So a transparent array-like interface, full support for automatic differentiation, and a comprehensive collection of tutorials, which is available online. Under the hood, this library, which provides support for symbolic matrices, combines an optimized C++ engine with high-level binders for PyTorch, NumPy, MATLAB, and R, thanks to Ghislain Durif. And of course, we very warmly welcome contributors for JAX, Julia, and other frameworks. To get started, you can simply download our library on pip, Python, PyKeops, and visit our website. So as a first example of how this looks like in practice, let me show you how to implement an efficient nearest neighbor search in dimension 50. So first, let me create large point clouds using standard PyTorch syntax. I hope that you're familiar with this kind of toolbox, but if you work with TensorFlow, NumPy, or MATLAB, the code should be roughly the same. So first we import PyTorch, then set the parameters of our program, so the number of points, 1 million, the number of points for the second point cloud, 1,000,002, and the dimension, so the number of features per point. So in this case, 50. I could have chosen anything. Then to create large arrays, large point clouds on the GPU, I just have to call PyTorch, ask it to fill large arrays with random Gaussian values, and load it on the GPU, using this CUDA magic word. Then, to benefit from the KEOPS acceleration, I simply have to turn my dense arrays into symbolic matrices using this line of Python. From pykiops.torch, import the lazy tensor wrapper and apply it on the arrays. You know, if you were working with sparse matrices, you would have used more or less the same kind of syntax, right? Now that the variables xi and yj represent symbolic objects instead of dense numerical arrays, I can create a very large symbolic matrix of square distances seamlessly using basic Python syntax like xi minus yj square dot sum with respect to the last dimension. I retrieve for free a 1 million by 1 million symbolic object that represents my matrix of square distances between the points x and y. Then, to perform nearest neighbor search, I just have to use an argmin reduction to perform my nearest neighbor query without memory overflows. Like, you know, here implicitly with this line, indices I equal dij.argmin with respect to the dimension j, I retrieve a standard PyTorch tensor, but without ever storing in memory the large 1 million by 1 million matrix, which would weigh a few terabytes in memory, and which obviously would throw me an out of memory error. Okay, so the script of the previous slide implements a very efficient nearest neighbor query, which is on par with the brute force CUDA scheme of the Feist library, okay, which is a reference library for nearest neighbor search on the GPU, which is something like 100 times faster than PyTorch. And the good thing, obviously, is that since it's Python, I can use it with any metric, you know, whereas Feist or most reference libraries for, you know, high performance computing are implemented in pure C++ and only support a handful of metrics. Using Keops, I can write the exact same program with, okay, the squared Euclidean metric that we've seen, but also the Manhattan metric. I just have to say that, no, instead of squaring my points and take the sum, I want to apply an absolute value and then take the sum. I can use a cosine similarity metric, or I can use a hyperbolic metric, you know, if I want. Going forward, Keops supports arbitrary formulas and variables with many reductions like sum, log sum x, k-mean, matrix vector products, mathematical operations that you can combine in your program like plus, times, but also square root, exponential, small neural networks, and advanced schemes like batch processing, block sparsity if you want to be clever, you know, and implement some kind of bounce hut strategy, octree, tree-based decompositions, and very importantly, full support for automatic differentiation. Okay, you can completely backpropagate through Keops instructions. I mean, it blends in super smoothly with PyTorch. So in practice, Keops lets users, so primarily me, my colleagues, you in the future, work with millions of points at a time without having to bother about low-level development. So to show this, I am benchmarking a matrix vector product with a n by n Gaussian kernel matrix between 3D point clouds. So what I'm doing here is I create 3D point clouds with n points. I create a Gaussian function, okay, exponential minus the square distance between the points divided by some bandwidth sigma. I compute the symbolic object which corresponds to this kernel matrix, and then I do a matrix vector multiplication between this big matrix, symbolic of course, and a vector. This operation, it's crucial to Gaussian process regression, for instance, or geometric deep learning, where it is called point cloud convolution. In physics, it's also related to fast n-body simulations, you know, when people want to simulate the galaxies and all that. So in this benchmark, I implement the exact same equations using NumPy, PyTorch, and Keops. So Keops used within PyTorch as an extension for PyTorch. And I display the runtimes in a log-log plot, okay? So the number of points n range between 100 and 1,000,000. And the time for the benchmark ranges between 1/10 of a millisecond, so super small, and 10 seconds. So you start to wait. So as you know, this type of computation out of the box, it's going to be quadratic. The runtime is going to be quadratic with respect to the number of points. If you don't implement any kind of clever, nice term approximation strategy or whatever, you just do brute force exact computations. You know that if you multiply the number of points by 10, so one step right, you're going to multiply the runtime by 100, so 2 steps above. And with NumPy on the CPU, runtime starts becoming a problem above 1,000 or 10,000 points. Now, as you're certainly aware, you can use PyTorch to leverage your GPU and speed up computations by 2 orders of magnitude compared with NumPy. So the blue curve here is what you get with PyTorch. You get very decent runtimes with 1,000 points. 10,000 points, it's still okay, just 10 milliseconds. But above 20,000 points, 50,000 points, essentially you start to get out of memory errors because the library cannot fit large n by n matrices in a contiguous space on your GPU chip. So that's a problem. But Keops completely solved this problem. Okay, so the red curves is what you get just by taking the same PyTorch code and adding this small lazy tensor wrapper to your variables before performing the computations. So what you see first is that you can scale up to 1 million of points in around a second. And this makes sense, okay? Because if you look at advertisements for modern GPUs, you see that they can perform a teraflop, so 1,000 billion operations per second. And this is exactly what we're doing here, okay? 1 million by 1 million is 1,000 billion operations per second. So without any memory overflow, so this is appreciable. And what you remark is that as soon as you are using more than 10,000 points at a time, you get a massive speed up compared with PyTorch, like something like a 30 times speed up compared with what most people in machine learning consider to be state of the art. And this is because essentially Keops implements very efficient. We are very careful with the management of the low-level memory on the GPU chip. Whereas this problem, it's not really a priority for the people who develop PyTorch. They're much more interested in convolutional neural networks, dense linear algebra. And so they, it takes a lot of effort to get optimal performances. They simply didn't do it. But now with Keops, it's there and you can use it in your programs. Okay, so obviously this is useful. So let me show you a few applications to generic machine learning problems before jumping to optimal transport. So first, Keops is, I think, pretty clearly a good fit for machine learning research. It's very easy now to implement scalable k-means or Gaussian mixture models using any kernel, metric, or formula you like. So you can implement those simple things, but also more advanced schemes like spectral analysis or UMAP visualizations in hyperbolic space. And I'm spending a lot of time adding tutorials. So every month or so, you have more tutorials that come up on our website. So this is nice to be able to scale up those kind of classic methods to real data sets and enable real-time processing. But I'm also a mathematician, So for me, it's very important to put this tool not only in the hand of engineers, of software engineers, but also in the hand of mathematicians. Let them see that now with the advanced tools that we have through PyTorch, Keops, we can implement very large-scale simulations of our methods using simple Python scripts. And this allows us to focus on our models, our results, and theorems, while having very fancy visualizations at the same time. So these images, they are produced not by me, but by a friend of mine at Imperial College, who's very interested in, simulating swarms of birds or of spermatozoids in 2D. And you see that, yeah, even if you have pure math background, using just simple Python script, now you can have real-time simulations, essentially, of those kind of systems of interacting particles with 100,000 swimmers at a time, and it's going to scale. So you can also do fancy things like packing problems in 2D, collective Monte Carlo sampling, etc. Okay, maybe an application that is more critical to machine learning research are all the kind of applications that revolve around Kriging, spline, or Gaussian process, kernel regression. So this theory, I don't know if you're familiar with it, but it's a standard tool for regression that corresponds to all those kind of plots, where you have data samples and you want to find a curve that interpolates between those samples and get uncertainty bounds, okay, in the regions where you don't have samples. So you have loads of, obviously, statistical literature that is devoted to this kind of problem, but under the hood, from a computational perspective, all these theories come down to the resolution of a kernel linear system. To get this kind of plot, you need to solve a linear system, big linear system, where your matrix is a kernel matrix. So something that can be represented using a Cheops lazy tensor. And the good thing is that we've really put a lot of effort into making sure that our Cheops symbolic tensors, just like sparse matrices, could interact well with the research community in this field and the standard libraries. So you can feed those lazy tensors to standard solvers, like the ones from the SciPy library or the GPyTorch library. And in practice, okay, so these are benchmarks that were performed by the GPyTorch authors. On the 3D road data set, like you have 300,000 points in dimension 3, you're trying to solve a big interpolation problem, and a task that was taking them 7 hours with 8 GPUs, now just by switching to a Cheops backend takes 15 minutes with 1 GPU. So what this means is that people in the community have been able to scale up their theories and their algorithms to much larger data sets than before. So for instance, I'm very happy to see that we've been able to help like people in Genoa and in Paris who've recently published a paper at NeurIPS, like kernel methods through the roof, handling billions of points efficiently. Okay, now using both Cheops and very clever math, okay, that I did not contribute at all. Like they are really developing very clever methods. People are now able to solve 1 billion by 1 billion kernel linear systems in reasonable time on reasonable machines. So that's pretty cool. And in my postdoc, in the context of my postdoc, which is made at Imperial under the supervision of Michael Bernstein, I've worked a lot on developing data-driven methods on point clouds and proteins. So why? Well, because using Cheops, you can implement very fast k-nearest neighbor search queries, so you get local interactions, but also really fast n-by-n computations. You can let all the points in a point cloud interact with each other in a reasonable time, while having all the perks of good deep learning libraries like heterogeneous batches, octree-like accelerations, etc. So if you're interested in this kind of problem, you can look at this paper. Okay, just go on my webpage, and we describe an architecture to process proteins that computes curvatures, perform quasi-geodesic convolutions on protein surfaces in very, very short time. So around 1,000 times faster than what people were used to just 1 year ago. So that's fine. But now, how do we link this to optimal transport? Well, I think that Aude and Anton have already spent quite a lot of time discussing optimal transport, and it's a fairly short talk. So I'm not going to dwell into optimal transport theory, but just let you know that using Cheops and a lot of clever math that has been done over the last decade, we now have access to very fast, scalable, and robust optimal transport solvers that you can just import in your programs to experiment with the kind of ideas that Aude and Anton have shown to you, okay, the past hour. So first, the question that we should ask ourselves as pragmatic researchers is, how do we solve the optimal transport problem? And this is a question that has been very important in applied mathematics and computational sciences since at least the 1940s. And if I had to make a kind of pragmatic literature review, I would, take out around 10 papers, the key dates for discrete optimal transport with endpoints. So the first one is really the paper by Kantorovich, who showed that, okay, to solve an optimal transport problem, you could think in terms of dual variables. You don't have to optimize on a transport plan, but really on just two dual variables that have the same memory footprint as your input data. So, I mean, he showed that optimal transport could be manageable. And then in the 50s, you have people who started developing cubic algorithms, like the Hungarian method. Then in the 80s, you have Dimitri Bertsekas, those kind of people on the East Coast who really made a really well-developed theory about the auction algorithm and the first quadratic algorithms, okay? Algorithms that scale in n square to solve the optimal transport problem. Then in the 90s, people kind of invented or reinvented the Synchron algorithm using annealing. They call this method self-design. It was really very fast, still in n square, but very efficient, loads of guarantees, and it was a big hit, in the computer vision community. So if you look at those papers from around 20 years ago, published at CVPR, it's called robust point matching, and it's essentially more or less the same thing as what Aude showed us, an hour ago, but not in a statistical setting, but for computer vision, like using Synchron as a loss function to register point clouds with each other. And, it worked. So, okay, so that's kind of history, people that I don't know personally. But then what happened is that, 7 years ago, Marco Couturi, once again, kind of rediscovered this method and realized that it streamed super well on the GPU. And this was really important because it motivated a whole community to work on the problem, try to find accelerating strategies to go faster than ever before. And so over the last decade, you can look at papers by Quentin Mérigot, Bruno Lévy, Bernard Schmitzer, who kind of improved upon this method and designed multi-scale solvers that really scale in our log linear algorithms to solve the optimal transport problem, at least in favorable settings. Today, I also spent quite a lot of time in my PhD thesis to study these questions. And now I can say we have access to very, let's say, satisfying schemes like multi-scale Synchron algorithms on the GPU that really behave as generalized quicksort algorithms. Because optimal transport, really it's sorting, but in dimension more than one. Okay, you have two distributions of points, you try to assign them to each other, just like you would sort two collections of samples on the real line. It's a bit more difficult because we don't have this kind of clean 1D structure of the real line, but we still have access to very good schemes. And now I can tell you that you can scale up optimal transport even to anatomical data, like, fine-grained point clouds, because the progresses of the last decade add up to something like an acceleration by 2 or 3 orders of magnitude compared with the basic Synchron algorithm as it was, let's say, presented by Marco Couturi 7 years ago. Okay, if you take this basic algorithm, implement it using Cheops, you get a speed up. You add a kind of annealing heuristic, you get another speed up. And finally, if you're in a low dimensional space, you can use some kind of multi-scale strategy and get yet another speed up, which means that, if you combine all of these ingredients together, you can solve optimal transport really fast. So let's say that if I want to solve optimal transport problems with a precision of like 1% on a modern gaming GPU, so something that costs like 500, 1,000 euros, then you can solve a problem with, let's say, 10,000 points in 50 milliseconds and 100,000 points, so, this kind of level of detail in really a tenth of a second, a fraction of a second. So obviously now we're very happy with it, but we understand that all those tricks, start to be a bit hard to implement for people. So it's very important for me to package this literature in a way that is accessible to the wider community. So if you want to try out those very efficient solvers, you can go on our website, okay, and visit the geom loss library, which is really called geometric loss functions for PyTorch, which implements very fast Synchron divergences, the ones that Aude showed us an hour ago, but also kernel losses, like MMDs, Hausdorff distances, etc. Because I think optimal transport is fine, but other other tools are fine too. I'm definitely not advocating for using optimal transport in all settings. So you can see, okay, like it's fairly standard PyTorch syntax. I just create 2-point clouds. I create a loss layer, just like you would create a cross entropy loss or something like that. And you just have to call it on your point clouds and you're done. Okay, and you can leverage those fast schemes. So, okay, it's a library. I've really put a lot of effort in it, like in 2019, so 1 year ago. Then I put a lot of effort in KeyOps, and now I'm back to active development of those optimal transport solvers. So you can expect that, okay, in 2 months maybe, there's going to be very efficient support, not just for point clouds, but also for images, meshes, and generic metrics. Okay, if you want to do optimal transport in hyperbolic spaces, then you'll be able to do it. And that's fine because, okay, just to let you know, my first motivation is medical imaging. That's really what I'm truly interested in, computational anatomy. And I hope that, in the future, I'm working with many people at King's College in North Carolina or in Paris to try to leverage those schemes and make them usable for people who deal with real data, real 3D data or in higher dimensions too. So just to let you know, okay, I'm talking a lot about machine learning, but this is really what I'm interested in for real, let's say. So about future improvements, well, I can tell you that KeyOps and geom-loss, they are pretty fast. They are very memory efficient. This is important. Like you have a linear memory footprint. Just the kind of memory footprint of these schemes is the same as the one of your data. There, you should never get memory overflows if you use KeyOps and geom-loss. They are versatile. There's a transparent interface because I strongly believe that it's important, to give freedom to researchers, and they are fairly well documented. But the main downside is that they are really optimized to work in low dimensional spaces like dimension 3, 10, 100, but beyond that, okay, it's not that efficient. So it's a bit of a warning. We can discuss it together if you want. You have tricks to accelerate things in dimension 1000, etc. But it's not what I focused on. So in the first half of 2021, so in the next 6 months, the main improvements that are going to be pushed in the main libraries, they are going to be approximation strategies inside KeyOps, like Nystrom rule, those kind of things, and support for grid images and Wasserstein barycenters in geom-loss. So about the roadmap, it's important for me to let you know, I present those tools, but I've worked on them for something like 4 years now. And there's still a lot of things that remain to be done. So just to let you know that it's an ongoing research project. And really, okay, 4 years ago, when we started working on this project, when we realized, okay, this is doable with the tools that we have, we published several papers, okay, proof of concept papers in conferences with online codes that allowed us to get first feedback from the community, realize that, okay, it's something that can be used by people. And now, over the last 2 years, we've made a lot of effort into making sure that now the libraries are pretty stable. Like KeyOps is very stable. geom-loss is going to be stable in a few months with solid theorems, like a lot of theoretical work too, to make sure that we're not doing complete garbage. We're using robust schemes and well-documented API. So I think that now, if you go on our website, it's useful for people like you, like people like graduate students, etc., and people who develop libraries. So we're in touch with many people who develop higher level libraries and kind of helping them to rely on KeyOps to speed up their computations. But now the main challenge for us going forward is going to transition this kind of stable research library into something that is mature, something that is really well documented with real applications papers, full tutorials for biologists, doctors, etc., so that it can work out of the box for people like undergrad students, engineers in companies. And really the hope, the target is that in 2-3 years, these tools are going to be standard, like a standard extension for PyTorch, NumPy, MATLAB, that's going to enable people to do real thing in the real world, like genuine clinical applications, etc. So that's really the target, and takes a lot of time, but we're very hopeful that it's going to happen. So as a conclusion, the key points really, the first main key point is that symbolic matrices really are to geometric machine learning what sparse matrices are to graph processing. Okay, so with key-ops, in a wide range of settings, like every time you manipulate distance matrices, this kind of objects, you can hope to get a very sizable speedup against, let's say, PyTorch, TensorFlow, or JAX. You know, it's 30 times speedup. It's not 30%. It's really orders of magnitude faster. And it's something that really surprises people. But I mean, it's really true. Like GPUs are much, much more powerful than mathematicians realize they are. Now, optimal transport, it's generalized sorting. As Aude explained to us, it's nice, like you get geometric gradients, and now we have very fast log linear solvers in most settings. So we hope that it's going to be more mainstream than it is today. And finally, you know, for me, it's important to say that these tools are meant to be used by researchers, like mathematicians, geometers, statisticians. I think it's a bit of a shame that people have come to believe that GPUs are only good to do matrix vector products and convolutional neural networks, but it really isn't true. Okay, GPUs, they are much more versatile than you think they are. Yeah, you have to remember they can be used in video games, you know, to have those super real-time, incredible simulation of the physical world. Okay, they are very, very powerful chips. And I think that as academic researchers, we should try to provide fast GPU backends to mathematicians, you know, going beyond what Google and Facebook are ready to pay for in TensorFlow and PyTorch. You know, these libraries, they are great, really great, but they cost a lot of money to develop from Google and Facebook. And so naturally, the only schemes that are really optimized are the ones that are necessary to the business models of Google and Facebook. So mostly image processing and natural language processing. But I think if you're doing something else, like medical imaging, geometric statistics, yeah, you have to realize that maybe vanilla PyTorch is not going to be as efficient as it should be, but it's not a problem. Like there are other people, there's actually a fairly large community of people who try to kind of provide add-ons for the main frameworks to make sure that all fields in applied math and machine learning kind of evolve at the same time, not just image processing. So as a conclusion, you know, I hope, let's say I believe that key-ops and geomloss are going to stimulate research in many applied fields, like clustering methods, like k-means, data representation, like UMAP, kernel methods, obviously, Gaussian processes, geometric deep learning. Okay, so that's what my postdoc is about. Geometric statistics, like if you want to do statistics in Riemannian manifolds, these kind of things, and maybe even natural language processing. So what do you think? You know, it's really a discussion that we are going to have with many people over the next 1-2 years, and to help kind of foster a good environment. You know, we've made sure to document, to put a lot of tutorials online for these tools. So if you're interested in all of this, you can go on our website and you can read my PhD thesis, okay, that I defended maybe 6 months ago, back in July, geometric data analysis beyond convolutions, and that you can access there. Okay, so that's kind of it. So it was a bit of an advertisement, sorry, for all these tools, but really, you know, we've put a lot of effort in this kind of low-level work, you know, in the cave, you know, in a sense, to accelerate those mathematical computations. And now we really hope that you're going to use them. Okay. So yeah, if you have any questions, you're very welcome, obviously.
Yeah, thank you so much, Jean, for your talk. I think it's always nice to have people like you in the community trying, you know, to develop libraries that make us researchers unable to compute things faster. Is there any question maybe in the audience?
I have a question. I'm sure you've had this question a lot, Jean. Thanks for the talk, by the way. But so everything you have is working with PyTorch. Are you working on an integration with TensorFlow? Because there's like half of the community working with PyTorch and half.
Yes. So okay, so I mean, it's a big question. Okay, you know, for people who don't know, the problem is that you had a standard for Python, which was NumPy. Okay, everyone was happy on the CPU, like very standard protocols, and then kind of GPU started becoming usable, and many different libraries have started developing kind of their own GPU backends. Okay, and the thing is that TensorFlow, it's developed by Google, just like JAX. And at Google, they have a kind of philosophy where they want to integrate everything within their own pipeline, which means that it's not very easy to kind of provide a new package that accelerates TensorFlow. You know, TensorFlow, it's more like you have packages who rely on TensorFlow to do interesting things, like GPFlow, those kind of things. But it's not very easy to kind of contribute to it without working at Google. And in this sense, the philosophy is very different to PyTorch. You know, the PyTorch authors at Facebook, since the beginning, they've really made a lot of effort to foster a community, documenting things very clearly for people like me, you know, who want to contribute, and kind of having an open community. So that's why at the moment, yeah, it's PyTorch and NumPy and MATLAB and R only, not TensorFlow, but you know, mostly because TensorFlow is not that open to external contributors. So now, obviously, it's a problem for everyone. And the people who develop TensorFlow, they are very aware of it. And so I know that what is happening right now at the moment is that there's kind of a consortium who is starting to be created, where the main authors for PyTorch, TensorFlow, scikit-learn, NumPy, and all that, they are kind of all coming together and saying, okay, we really should have a standard kind of interaction protocol for kind of GPU arrays, so that to make it seamless, so that you can use Matplotlib seamlessly with tensor arrays, TensorFlow arrays, PyTorch arrays, etc. So what I hope is that they are going to, you know, they have started to publish like technical notes of what they want to do. And what I hope is that over the course of 2021, they are going to agree all on a standard protocol, and then TensorFlow, they are going to implement it. They are going to implement an easy to use kind of, they are going to open the door essentially to their engine. And so it's going to be much easier for us to provide a TensorFlow API. You know? So yeah, so that would be my answer. That would be my answer. And maybe, you know, so yeah, we are also starting to discuss with the people who develop JAX, like, you know, Mathieu Blondel, you know, I've kind of already talked to him quite a lot about it. And so, yeah, so it's something that everyone is aware of. Yeah, we have to remember that all those libraries, they are very young, okay? Like PyTorch started to become usable just 4 years ago, which is fairly short, actually, a short amount of time. So yeah, I hope that within a year or two, hopefully the issue is going to be solved, and we're all going to be able to use those different libraries seamlessly without having this kind of weird clusterizations of the community, which is totally unnatural. Yeah.
Yeah, I was just saying, any more questions, but maybe you already have other ones. Aude, I don't know.
No, that was my main question. Thanks.
So I have one question. Thanks, Sean, for the very nice talk, and for kind of contributing to the community with such an impressive library. When I was working with the Bayesian approach to OT with the stochastic cost, I run into the problem that sampling in high dimensions is very kind of costly and slow. So motivated by that, is there kind of, have you thought any links with the probabilistic programming languages there are? So with PyTorch, there is Pyro, and I think you had a mention about R. There is Stan is the kind of mainstream choice. So yeah, are there any tutorials on this, or kind of do you plan on?
So not really. Okay, so the thing to know is that, okay, like this library, those libraries, we've developed them, like I've developed them with colleagues like mostly Benjamin Charlier, Joanne Glonès, and kind of on the theoretical side, Gabriel Perret, Alain Trouvé, François-Xavier Vialard. and Thibaut Séjourné. And the thing is that we're all more like geometers than statisticians, really. So, you know, our main motivations usually are in geometry, medical imaging, these kind of things. And obviously, like, we're very open to statistics. We'd like to know more and all that, but it takes a lot of time. And kind of the first applications that we target are the ones that we understand very well, like kernel methods and kind of geometric deep learning, these kind of things. So just to let you know, I believe that those tools can be useful in many settings, and that's why, you know, I've started to work. It was kind of a holiday project with friends. I started to work on this kind of collective Monte Carlo sampling, you know, developing small toolkits, publishing small papers. I mean, they are not completely yet published, but they're going to be available soon. You know, to say, okay, we can use KIOPS to speed up those kind of strategies and methods that are so common for statisticians. But then, yeah, it's probably going to take time before we get integration with things like Stan and all that, because I don't know them, they don't know me, or they don't know us. And so, yeah, you know, I'm hopeful. You know, I've presented these things in many conferences to you now, and you know, we are having discussions with people who develop many libraries. Maybe, yeah, one that you may know, it's like GeomStats, you know, these kind of things. Geometric statistics, PyTorch geometric and all that. And so I hope that, yeah, in a few years, the field is going to evolve. Okay, but it takes a lot of time, obviously. And you always have the question of how motivated people really are. You know, I think to kind of make the investments of going into GPU computing and all that, you need to have fairly large data sets, at least more than a few thousand points. You know, all this work was motivated by the fact that I wanted to use optimal transport with 3D shapes, okay, in a setting where you have easily 100,000 points at a time. And so because we had this very strong motivation, I kind of devoted 3 years of my life to make it work. But if you're working more in, let's say, a stochastic setting, you know, like Aude is doing or you are doing, using typically a few thousands of samples at a time, maybe you don't really want to bother with that, and you're more interested in getting statistical bounds, etc. So yeah, so you know, for me, you know, it's clear that those tools are going to be important and interesting in, let's say, geometrical fields and maybe computational physics, computational biology. And in statistics, it's a community that I don't really know. You know, I've been to AI Stat, I've met you, I've met, you know, I know Aude and all that very well, but I don't know if there is that strong of an interest in the community for scalable schemes. So what's going to happen is that the tools are going to be out there. So they are going to be usable by people who have, let's say, a few weeks of spare time on their hand and who want to really scale up their schemes. But is someone really going to invest 1 or 2 years of work into making a user-friendly library for this? I don't know. I hope so. But yeah, it takes a lot of time. And the thing is that, you know, maintaining a library takes a really large amount of time every day, you know, answering questions and all that. And the things that, for instance, I'm kind of already stuck with those kind of geometric problems. So you need fresh blood to come in and be interested and want to develop new toolboxes. So that's why, you know, I'm working with groups of students at Imperial in Paris and all that to try to foster a new generation of scientists and computational developers, scientific developers. But it really happens on a case-by-case basis. So who knows?
Okay, thanks a lot.
Okay, I think we will end the seminar series now. Thank you again and again, Aude, Anton, and Jean, for speaking to the seminar. It was very, very nice to have you. I think we're very lucky. And
thank you very much.
Thank you, Alison, for organizing everything. And I was really happy to hear about Jean's latest research because we know each other